When you look at your car's speedometer and read 60 miles per hour, what does that number actually mean? Velocity is distance divided by time. But at that exact frozen split second, you cover virtually zero distance. So, how can something have a speed at a single, precise moment? Behind this seemingly simple question lies one of the most powerful intellectual breakthroughs in human history: the derivative. It is the absolute bedrock of calculus. Developed independently by Sir Isaac Newton and Gottfried Wilhelm Leibniz, it allows us to move past mere averages and calculate the exact instantaneous rate of change. In the next 5 minutes, we will unlock this mathematical masterpiece, moving from intuitive geometry to formal calculus. Let's look at a function, f of x. If we want to find out how fast the function grows between two distant points, we calculate the average slope. We draw a straight line through both points, called a secant line. The slope of this line is simply the rise over the run, or the change in y divided by the change in x. Here, h represents the horizontal distance between our two chosen points. But what if we want to know the slope at one exact single point? Classical geometry fails us here, because a slope fundamentally requires 2 points to exist. This is where the genius of calculus comes in. We don't make the distance h equal to 0, because dividing by 0 is mathematically illegal. Instead, we make it infinitely small. We mentally push the second point so close to the first that the distance approaches 0. The secant line, which cuts through the curve, seamlessly transforms into a tangent line, touching the curve at exactly one isolated point. Formally, mathematicians define this dynamic process using a concept called the limit. The universal definition of a derivative is written as: this equation, known as the difference quotient, looks intimidating, but it tells a beautiful and simple story. Calculate the average slope between 2 points and observe what specific value that slope converges to as the distance h shrinks towards 0. Let's prove this with a concrete example. Consider the function f of x equals x squared. Let's substitute it into our limit formula. By factoring out and canceling the h from the numerator and denominator, we are left with 2x plus h. Now we apply the limit. As h approaches 0, that remaining h completely vanishes. We are left with exactly 2x. We have just mathematically proven that the derivative of x squared is 2x. At any given point on that parabola, the instantaneous slope is exactly double its current x value. The true power of this concept is that the derivative does not just give us a single number for a single point. It gives us an entirely new function, denoted as f prime of x. It acts like an X-ray blueprint of the original graph. When the original function climbs upward, the derivative is positive. When the original function slopes downward, the derivative is negative. And at the critical stationary points, the peaks and valleys where the curve becomes perfectly flat for an absolute instant, the derivative is exactly 0. This single property forms the foundation of all optimization algorithms, from economics to machine learning. For notation, we frequently use prime notation, f prime of x, introduced by Joseph Louis Lagrange. However, in physics and advanced engineering, you will constantly see Leibniz's notation. This notation serves as a permanent reminder that a derivative is always a ratio, an infinitely small change in f divided by an infinitely small change in x. Without the derivative, the modern world would quite literally grind to a halt. Every time an aerospace engineer calculates a rocket's trajectory, an economist forecasts marginal revenue, or an AI algorithm trains deep neural networks, calculus is working silently in the background. The derivative allows us to take a chaotic, constantly moving universe and slice it into precise, predictable snapshots. If you enjoyed this journey into calculus, hit the like button and subscribe to the channel. Let me know in the comments below. Which mathematical concept or rule should we demystify next? Stay curious, and I'll see you in the next video.